Okay, so we were doing nonlinear structures, right? So it's just reminding you the typical evolution that I drew there. Let's do a very crude model just to set the stage. We stick with Zeldovich. Remember we said in Zeldovich the nonlinear density is 1 minus d over lambda. And in Zeldovich the 3 lambdas could be different from each other. But I said if the 3 lambdas are the same, that's like a sphere. So what is the evolution of a spherical object in the Zeldovich approximation? And so that's a kind of a trivial thing, right? Because you'd say I have 1 minus d growth factor lambda cubed because there are 3 sizes and they all have three directions, okay? And the sum of the 3 eigenvalues is what we call linear theory density. And so that means this guy is really the linear density over 3 because they're all the same. And so this has a very easy form to remember, right? The nonlinear density is 1 minus the linear density over 3 raised to minus 3. Okay? So now we'll keep this in mind. And now we'll do the evolution of a spherical object where we do it properly, where we account for the fact that the acceleration is changing as the sphere gets smaller. Okay, because Zeldovich, remember, is just straight line. Okay? So spherical evolution. So this one is F equals ma, right? Force is mass times acceleration, so the acceleration is the force. The force is the gradient of a potential. Okay? And so here's the potential if there was no lambda, and the lambda term looks like this. Okay. Okay. And then all I did is wrote this in cosmology units. So I said you can replace the m by 4 pi r cubed over 3 times the density. And the 4 pi g over 3, if I put an h squared, then I should keep the h squared out here. Then this guy is like the critical density. And so rho divided by the critical density is what we call omega matter. And so this guy is omega matter times h squared times r plus lambda r.
We are assuming the universe to be flat here.
We're just putting flat cosmological constant. Okay. All right. So, okay, let's not worry about modified gravity because Anjan hasn't talked about that yet. So now let's do a very crude analysis of this kind of system. Okay, we'll write down the exact solution soon. So it's a differential equation that can be solved. Okay, but before the solution. Okay, so so remember you have if there were no lambda, then the object will be trying to shrink because of gravity. And lambda is an expansive, it's like a repulsive thing. Okay, so it comes with the opposite sign. Lambda is constant in space, constant in time, so it's just a number. And then it scales with r because this was already there when Anjan wrote out the Friedmann equation. Okay, so it's the same equation. And so when Anjan wrote it out, he was writing it for a model, a cosmological model. Now we're writing it for a patch inside a model, right? But it's the same idea. Right?
I was always confused about where this is. So this is a ball of dark matter in a background universe.
In a background universe.
And the ball is growing under the influence of its own mass.
Yes,
gravity.
That's right. Yeah.
So
okay.
Omega here is the omega of a hypothetical universe where the uniform density is equal to the density of the ball.
So explicitly what it was, so what did I do? I took the m, and I wrote the m as a 4 pi r cubed over 3. times the
but this
density.
M is the total mass, I mean uniform plus excess. In the ball.
Uniform plus excess.
So that's what I was saying, that this omega is...
That's right, yeah. So this rho, that's right. So that's good, okay? So by writing it this way, remember I have a choice about how I want to describe evolution. When we do Zeldovich, we imagine you started on a uniform grid and the velocities are driving everything. And so in that case, you would write it like this, okay? But we'll have to ask where's the velocity initial condition entering? And that velocity initial condition will come in because this is a differential equation, and so you have to define the initial conditions when you solve. Okay. Yeah?
Just can you explain the motivation behind this? Means spherical evolution means you are considering some of the mass or some of the matter in some sphere.
Yes.
And you are considering some fluctuation in it.
Yes.
And then you are just try to find out that how the structure will be formed in this limited space.
Yes.
No, I thought
But we're thinking that it's going to be very trivial. We're thinking that it's going to, if this thing is dense, it's going to shrink. Okay? But if we're saying it's an average density, then we will think in the language of Zeldovich that the velocities are set up so that it's starting to shrink and then it will keep shrinking. Okay? So that's all. So it's a patch that either the density is slightly bigger than the background, as a result of which it's going to shrink, or it is the same density as the background, but the initial velocities are all inwards, and so it's going to shrink. Okay?
So right now on this, the next slide, you haven't put in the perturbation yet.
I haven't put it in yet.
It's just a
It's just
patch
to-
inside
yeah.
the universe, which happens
That's
to
right.
be spherical.
Yeah,
And you're looking
That's
at the
right.
mass inside it.
that's right.
Right?
Yeah.
The lambda has been put to avoid the collapse.
The lambda will make it harder to collapse. That's correct.
And
Okay?
here also we consider some presence of dark matter or not. We are not making
The mass is everything, so it
Mass
includes
is
dark
everything,
matter.
no?
Yeah,
This is all dark.
yeah. This includes everything. So, yeah. Yeah, it's mainly dark matter. Yeah, that's right. Yeah, it's the sum of all of them, but it doesn't matter.
Is the rho is the background density?
The way I've written it here, rho is the background density, okay? And I'll be slightly ambiguous about which it is, because in the next slide, I'm going to change a little bit because the analysis is a little easier to see. But I've tried to set up with Zeldovich to tell you I'm allowed to translate between thinking of the perturbation as background density but a velocity perturbation, or no velocity perturbation but I'm slightly denser than the background. Those two are equivalent. Okay? Okay.
This lambda is some constant.
That's the cosmological constant. Yeah. It is, I guess, to be the cosmological constant, it would have to be omega lambda, and so there's some factor of 3 and stuff. But
Where did the
yeah.
R come from?
Because so the cosmological constant is when you write out Friedmann's equations, it comes like this. Okay, so and there's
linear repulsion kind of a...
it's like a linear repulsion. There's kind of a it's really I mean the linear repulsion is the physical thing we think of, but it's kind of a deeper thing. So that's what I've kind of written here. Okay, there was a fight when Newton described the force of gravity. He had a fight with Hooke, who was Hooke's law, because Hooke thought that he had invented a law, a force law, that could have stable circular orbits. Okay? But Hooke's law was the one of a spring. No, it increases linearly with separation, the force.
Both those
okay?
laws will give you stable orbits.
Those are the only two that give you stable circular orbits. And so it's no surprise that those are the only two that show up in GR. Okay? So the cosmological constant is a force that is linear in distance, and the other one is 1 over r squared, newtons. Okay? So that's the comment I have here. No? If you were interested in working with a theory that was not GR, then you suddenly have to start worrying about, so this guy is going to become modified, and that means that circular orbits are no longer stable, so you now have to worry about stability of solar system and stuff like that. Another way to say it is stability of solar system might provide an interesting constraint on these theories. Turns out it does, but it's not a very interesting constraint anymore because the constraints are so strong.
So then the
But
shape
in
of the
principle,
orbit is determined by the power of R, right?
the shape of the orbit is determined by power. That's
Because
right.
this
Yeah.
R will give you an orbit where the sun is at the center of the ellipse and not the
That's right.
focus.
That's right. Okay. So let's try to analyze this thing before we write down the full solution. Okay. And so one way in which something like this is solved is you say, I'll integrate this once with respect to time. Okay. And that's a little bit like saying I think of d squared r dt squared as d by dt of dr by dt. And I could have written d by dt of dr by dt squared. Okay? And dr by dt is like a velocity. So dr by dt squared is like a kinetic energy. And so one integral of this will be related to energy. Okay? And so that's all the algebra that has gone in here. Is just saying if I were doing an integral with respect to dt, so if I was doing dt here and I was doing dt here, and I do the integral, then I will get this combination which I call the energy, right? Because I'll get one term which is like a potential energy and one term that is like a kinetic energy. Okay? And so just to keep the math simple, I'm no longer using a cosmological constant. It just makes everything more complicated, but none of the fundamental answers change. Okay? And I will say in a second what is more complicated with the cosmological constant. So here there's some initial energy, and now I've chosen to write the energy as potential and kinetic, and the kinetic I've written as the Hubble, h times r. That's the speed squared, okay? And that means that I've not perturbed the Hubble expansion. So now I'm going to say the object is slightly denser than the background, so I'm going to write this as some 4 pi r cubed over 3 times the background density times a 1 plus delta. Okay? And that will be my initial condition. But my initial condition is an initial energy. Now what's going to happen is that these shells, so they're all background density times 1 plus some small number. So now they're all going to start to shrink because gravity is going to pull them together. All the shells will shrink until they all meet at the origin, meaning that thing shrank to 0 size. Okay? So the concentric shells are going to always remain concentric as they shrink. So the sphere is just going to change radius. That's all. Okay. And as it changes its size, energy is conserved. And so energy conservation is going to help us do this problem. Okay? So the first thing we can ask is, so with my hands I've been doing that it shrinks. But in reality what is happening, it's expanding like the background universe, but because it is slightly denser than the background universe, it's going to stop expanding as quickly as the background universe and it will start shrinking. So in physical coordinates it's going to do like this. And the rest of the universe outside will keep expanding. Yeah? So it will expand for a little while and then it will shrink. So that means there is a time when it has reached maximum size before it's going to shrink. At the time it reaches the maximum size, it has no kinetic energy. So it's all potential. And so we'll call that time, that event we'll call turnaround. And the energy at turnaround is all potential, no kinetic. And yeah.
During this evolution, we are assuming that the expansion of this overdense region is exactly same with the background.
No, it's a little bit less than the background.
Then can we use the age throughout for the photo region as well as for the background?
Sorry, so this is the initial. Then after that, the expansion speed will be different from the initial, but it's the same as, if I want to calculate what happens as I throw this up to go to the top, I can calculate how the speed changes at each instant. But energy conservation is a very powerful thing. I don't have to think about the speed changing at all positions. I just say, at the top, there's all potential, no kinetic, and I don't care about the details. Yeah? So that's the game I'm playing now. I'm saying I'm going to use energy conservation to guide the thinking about the problem. But you're right that at any time after the initial time, the speed is not given by HR. It will be less than that. Yeah? Less than that, less than that, less than that, till 0. Okay. Okay, so at turnaround, the energy is minus GM over the size at turnaround. But this one must be the same as the initial by energy conservation. So here I'm just writing them to be equal. Okay. And so then I'm going to try to put all the RIs. So I'm going to put Ri on the same side as the R max. Okay, so we're just rearranging this. And in rearranging that, we're doing, because I have an Ri squared here, this guy will have an Ri cubed, so there's an Ri squared here. Yeah? So that's the kind of game we're playing, right? We're saying, here I'm going to, if I write this as a 4 pi R cubed, all that stuff, I will end up with my cosmology units, okay? And so this is just the algebra of putting the Ri over R max here, taking this term. So I guess all I've done in this first step is I just divided this here, which means now I have to divide this here. So that's the dividing this here. And now I'm going to put the G, I will put my 4 pi R cubed, that kind of stuff, okay? And here is where I'm going to put the fact that the M is the 4 pi R cubed with a density that is different from the background. Okay? So what do we see? We see that the ratio of the initial size to the maximum size it reaches before it turns around depends on the initial overdensity. And we've done a Taylor series, so it is just proportional to the linear density, because this number is small, right? 10 to the minus 5.
This should be something like 3 times the perturbed density or something. Or some factor of 3 or cube or this. Because it's a linear ratio, and we are finding density kind of thing.
So right now, we're really just, we're not calculating the nonlinear density yet. We will do that. Okay? So right now, we're just asking what is the ratio of the size at turnaround compared to the size that it started with.
So right now, it's just some parameter which parameters this ratio.
The 3h squared by 8 pi g is also density dimensions. So ultimately, it's dimensionless.
Yeah, this is just dimensionless thing. But yeah. Okay, yeah. So this is just saying, that I want to know, did it expand 2 times, 3 times, 10 times, right, before it turns around?
No, what I meant was, if the radius expands 2 times, the density expands 8 times.
Yes, that's right. So we're going to do that kind of thing soon, but we're not there yet. Yeah.
When it expands, it is kinetic energy. And after it reaches a maximum volume, that is the maximum kinetic energy.
There's 0 kinetic energy, now it's all potential.
And then it starts increasing potential.
Yeah, and then the kinetic energy will start to increase again. Yeah?
This analysis is valid when the background cosmology is matter dominant.
Yes.
Otherwise, in the recent accelerated acceleration phase, this lambda will also.
Very good, right. So you're pointing out the reason why I set lambda equals 0 to do this kind of analysis. And the reason I set it to be 0 is that the cosmological constant is a constant. Okay? And that means that as my perturbation suppose I was keeping the cosmological constant term, okay, so there was some energy from the mass and kinetic energy, and there was some energy from the cosmological constant because the perturbation had some volume, so there's a certain energy density times this volume, okay? But now the perturbation is expanding before it turns around. So as it expands, the mass is not changing, the size is changing, the speeds are changing, okay? But because the volume is changing, I'm getting more dark energy in the volume. And so the energy is no longer conserved. And that just means you have to, you know how much it's not conserved because you know it's just the volume. So it's easy to calculate and account for it, but it just makes the analysis messy, okay? But it's a good point because there's a lot of interest in trying to constrain neutrino masses from large-scale structure. And so let's imagine that some of the mass was neutrinos, okay? Now neutrinos are different from cold dark matter, right? So let me put it a different way. In here, the kinetic energy was the Hubble flow. There was no term of random motions because it's cold dark matter. But neutrinos, they are hot. They are moving like this, okay, in all directions. But also the neutrinos, they're moving very fast. And so if they're moving very fast, then a small potential cannot trap them. And so that means that they're not trapped. That means there's a uniform sea of neutrinos that are passing through this patch all the time. So they're almost like a cosmological constant, except they have positive mass. And as the perturbation expands, it will enclose more neutrinos. So it will get more mass, so you won't have conserved mass. You have to be careful about that. And with neutrinos, it's a little more complicated because the cosmological constant in the simplest models is independent of time and space. The neutrinos, they're cooling. And so the energy that you're getting from the neutrinos, you have to be a little careful how you calculate that to account for the fact that they're cooling. Yeah? But again, it's technical problems, not conceptual. Yeah? But that is why to constrain neutrino masses well, we need to know lambda well. Yeah? In the spherical model, you kind of see this nice degeneracy between the two because they're competing in this framework.
What if there is a spherical collapse during the transition phase from lambda dominated to the lambda dominated? So what will the lambda value?
Oh, okay. No, okay. So it is possible to do this whole thing where we put it all properly. We don't have to do a step function for transition from. We just put the proper thing where the lambda is, where it's matter dominated early and becomes lambda at late times. You just put it properly and it all comes through. So it's just you will get an extra correction term that everything looks ugly, but you just do it properly. Okay. The time, if you want to know, the dark energy started to dominate at redshift 0.3 or 0.4, something like that. But if you were going to solve this and put in a dark energy term, you would just put it properly.
What are the time scales that are involved in this evolution?
The time scale? 14 billion years. Yeah. But we'll make that more precise, but that's the Hubble time. Yeah. But we'll see now, okay? What we have here is that how many times it expands before it turns around is related to how dense it was. Okay? So that's interesting, no? Because it means that if I have a patch that contained 10 to the 15 solar masses, and it was 10 to the minus 5 above the background density, then it will expand by the same factor before turning around as a patch that was 1 solar mass. Okay? So the mass is irrelevant. Okay? The density is controlling everything. So this is going to be really important. Okay? So that the amount by which something expands before it turns around depends on its density and not on its mass. Okay? So that's a non-trivial conclusion that is coming from energy conservation. Okay? You might have thought the big guys, they maybe expand factor of 3 before they turn around, whereas the little guys, maybe they expand a lot. But the thing that controls how much they expand is their initial density, not their mass.
That's valid only when delta is very small.
This is valid only when delta is very small, but we believe delta is 10 to the minus 5. Yeah?
So here, how do you define delta?
Delta is the mass is 4 pi r cubed initial over 3, the background density initial times 1 plus delta initial. Yeah? I can be even more careful if you want, and what I'm really assuming is that initially, compared to the background, it was dense like this by a small amount. This one is just delta, and this one is 1 plus delta.
Are you saying this is 1 plus delta or 6?
Or the picture that I'm drawing.
No, that is the expression. Capital delta is rho equal to capital delta into rho I bar, or the 1 plus.
Which is a fluctuation.
So the mass is a volume times a density, and the density is the total density. That's why it's 1 plus delta.
No, I am saying sometimes capital delta equal to 1 plus small delta. Is this that capital delta or the small?
This is the small delta. Yeah?
So this is just a fluctuation in density, no?
It's just a fluctuation in density.
Oh.
Yeah. Okay. And because it's denser, it's going to shrink. If it was underdense, it would expand. Yeah. The more careful statement is if the potential energy is more negative than the kinetic energy is positive, then it will shrink. Yeah. Okay. So, yeah.
At the turnaround radius, can we equate this equation to the effective cosmological constant at late times in order to obtain some constants on the time?
You want to set this equation equal to the cosmological?
At late times, so that can we obtain some constants? Is it right? I mean, is it?
No, I think you should just solve it correctly if there's a cosmological constant. And it's not hard to do. So maybe what I should do is I'll give you some notes where the cosmological constant case is done. But it's not, it's just messy. It's just not conceptually any different. So you should not be trying to play games with approximating how to put in the cosmological constant. I think it's not necessary. But, I mean, I never tried, but. Okay. So, after it turns around, it's going to shrink. And formally, it's going to shrink to a point. But we know that's not really what's going to happen. It's going to shrink and do this. And finally, there will be some object. And that object, we're going to say, is a stable object in virial equilibrium. And so we will say it virializes. And that means, for an object that has virialized, it means that the sum of the potential and kinetic energy, so the total energy, is, well maybe in virial theorem is minus potential is twice kinetic. Okay? And so that means the total we can either write in terms of kinetic or we can write in terms of potential. Here we're going to write in terms of potential because with potential we're going to get, the potential energy is a scale because the mass is not changing, so it's only the size. And we're going to conserve energy, which means that the energy at turnaround, the potential energy at turnaround, has to equal the total energy at virialization. And the total energy at virialization is gm over r and half of that. Yeah?
So this Virial theorem is defined in terms of time average quantities.
Time average thing, yes. Yeah.
If I have like, so the spherical collapse is happening, it can go like this, keep on doing this. Even then the things are bound, they are not running to the infinity, and my Virial theorem could do it. So but here when we are finding our Virial, that is a particular radius.
That's a particular radius.
Then the object is finally collapsed.
That's what I'm saying is how we are relating the time average radius, time average quantities to a particular value.
So we are assuming, so there's two ways to think of it, okay? You're thinking of a very complicated problem where you had this big mess, and so you have some particles doing this and some doing this, okay? But let's think of two extreme simple things. One is they're all on circular orbits, and the radius of the circular orbits is shrinking. And the other is that they're on radial orbits, but when they're on radial orbits, they obey Kepler's laws. When they obey Kepler's laws, that means that they go fast when they're close to the focus and slow when they're far. So they spend most of their time far. And so their radius is basically the maximum size they reach. That's the time average radius will basically be the big one, if it was a radial orbit. And if it was circle, there's no problem because it's circle.
So when we are defining our Virial, what is this?
Because we are taking this completely idealized thing, we're not worrying about these details, yeah? And so we're just saying that the final object, when it gets stable, the typical size of the orbits is going to be r virial.
Here we are not putting.
Sorry, so some of them will be in circles, some of them will be radial, and there will be a distribution of sizes, but the typical size will be this.
When we're looking at this from a physical point of view, does it mean that this thing is in equilibrium where the Hubble expansion is balancing out the collapse at all times?
I don't know if you would, I don't know if I'd say it was balancing out the Hubble, but it is something that has, it is no longer expanding with the, yeah, that's right.
What's the physical reason for that? Like, I'd like to think that the collapse is now balancing the force of the Hubble expansion. So you have an object which is looking to you like it's in equilibrium and it's stable.
Similar to why solar system is stable.
Exactly, it's the same thing. Yeah, it really is that it has detached from the expansion, right? And so the rest of the universe is expanding away, and it's, so in co-moving coordinates, this guy is going to keep shrinking, okay? And so that's why I was hesitant to answer about whether it's balancing the Hubble flow, because in co-moving it might have been keeping constant size, right, to balance the Hubble flow. So, so this is a thing that in co-moving coordinates would be shrinking once it's virialized, right? To virialize it was shrinking in physical coordinates as well, but then it virializes and then it's constant in physical coordinates, and that size is what we're calling the virial radius. Okay? So what happens when it virializes is it satisfies this thing, okay? And so the potential and the kinetic are balanced. So, you know, I should have added, I guess, some notes. There is an equation which is what is the equivalent of energy conservation in an expanding universe, and it's called the cosmic energy equation. And the cosmic energy equation, so it's the thing that is like writing down energy conservation. You see two terms, and one term is this term, and there's another term which is a term that is when you're not virialized, okay? And so you can see the transition between these two things. So this is the equation that is used to check energy conservation in simulations to make sure that they are conserving energy. And I think this would address some of the question of why, even though it's in an expanding universe, once it's virialized, nothing happens. So in the break, come and talk to me and I can show you that.
You are not putting any limit that you have to take that much of maximum mass and radius. Because if it is very massive, then gravity may overwhelm and it will end up to the singularity also.
No, so the only thing that matters so far, right? The only thing that matters is the initial density. Okay. Now we're going to ask when it comes and it turns around and it starts to shrink. Okay. Then it will do something. And the final object, I agree that if you're talking about stars and it will go through, it will make a star and go through stellar evolution, and then finally it will maybe become a black hole. But that's not what we're talking about, right? We're talking about much bigger than that. We're talking about galaxies, 1 billion stars, yeah? So we're talking about much bigger structures. That's an estimate that we should have done when Anjan did his calculation. He wrote down the Jeans criterion for the oscillations, but we didn't estimate the mass. That mass is 10 to the 5 times the mass of the sun, something like that. So it's pretty big. Okay. But so the main point is the only thing that matters is the initial density. And then energy conservation for the virial guy means that it shrank by a factor of 2 from its maximum size. So that's also a non-trivial statement. Again, that factor of 2 is the same whether this was a huge object or it was a small object. They all shrink by a factor of 2. Okay? So again, energy conservation has simplified what could have been a very complicated problem. And so, of course, once you have...
Now that you're assuming that it does...
That it does virialize. Yeah.
It may not always.
It may not always. So if you want, we will go to simulations at the end of this and we will check if the things are virialized. Yeah. So this is a very non-trivial statement, right? That you just shrink by a factor of 2. And because the ratio of the biggest size to the initial size depended on the initial density and not on the mass, the ratio of the final size to the initial size depends on the initial density and not on the mass. Which is like saying, because the ratio of the initial and final size, if I cube it, that's the ratio of the initial and final volume. But the initial volume is the mass multiplied by background density. The final volume is the final volume, so that's the nonlinear density. And so the nonlinear density will be the same for all objects, whatever their mass, and what that number is determined by the initial density. Okay? So this is a very non-trivial statement, that all nonlinear objects should have the same density. That's not obvious when you start the calculation, right? But that's coming from energy conservation. Okay? So now we can ask, so what happens if the initial density was very big? Very big doesn't mean 2 or 3. Very big means 3 times 10 to the minus 5 instead of 2. Okay? So if it was very big, then it means that this object expanded and shrank quickly. If it was not very big, it expanded bigger and then shrank. Yeah? And so if I'm interested in objects that have completed this cycle today, they had to have exactly the right density initially to complete this exactly today. If they were denser than that, they'd finish this cycle in the past. They virialized in the past. And if they were less dense, they will virialize in the future if they are overdense. Yeah? And so that's the cartoon, right? They expand, turn around, shrink, and they virialize at half their radius, half the turnaround radius. Okay? And it turns out that that equation of motion, the collapse is symmetric with the expansion. And so the time to collapse from turnaround is the same as the time from the start to turnaround. So it's just double the time. Okay. Okay. So here's a check that this kind of argument is right. In simulations, what was done was we found objects. So in this case, we found one object that had a density. Okay. And we asked, so it's some multiple of the background. It happens to be of order a few hundred times the background. And we asked where were the particles that make this object at an earlier time. So today the object was small. At the earlier time, they were spread out over a bigger region, a roughly spherical region. Okay, they were spread out here. At the earlier time, there are lots of small pieces inside it. Each of these pieces is the same multiple of the background universe at that earlier time. And they're all the same density. The big ones are the same density as the little ones. So the big mass is the same density as the small mass. Yeah, so this question of the generic prediction, is it okay? It is borne out in the simulations. Yeah.
So this is where you get the hierarchical formation?
So this is the hierarchical that the little guys, they merged.
The same, and then they come together to form bigger ones.
Yeah, so we're going to do more of the hierarchical soon. I'm already late, right? People were supposed to jump up and down at 11:10, right? But we're almost done, okay? So let's go back, right? So we have a critical density that's the same for all objects. That density is, so if the initial density was big, the object collapses early. If the initial density was small, it collapses late. The objects that collapse, they are always the same multiple of the background density at the time that they collapsed. Yeah, because the ratio of this to the initial size is a measure of the final to the initial, right? And final to the initial is a density. I could have called them co-moving, and then it would have been a density with respect to the background. Okay. And so, what happened? There we go. So this is the exact solution. Okay, it's a differential equation. We could have done it all exactly, right, without doing the energy conservation. Right? So I've just written out what the exact solution is. Okay, it's one of these differential equations where you get the size as a function of some parameter, the time as a function of some parameter. So now you can plot R versus T. Okay, and it gives you this kind of curve. Okay. It's not very illuminating. Okay, I mean you just have to work it through, but this is very, very well approximated. So let's look at this. This is the nonlinear density as a function of this parameter. The reason I've written it this way is that this is the way we wrote Zeldovich, except Zeldovich was 3. And so the question is this number 3? And because this is the correct calculation, if it's different from 3, that's telling you how bad Zeldovich is. Yeah. Okay. And so that number, I have it on the next slide. That number is 1.68. It's like half of 3. Okay, and that makes sense. Zeldovich is saying that the density had to be higher to collapse. The initial density had to be higher to collapse by the present, because Zeldovich is not updating the velocities. You know, as they get closer, they will accelerate faster towards each other. And Zeldovich doesn't do that. And so Zeldovich thinks, oh, to collapse by the present time, you had to be denser. Whereas the correct calculation says you didn't have to be so dense. Yeah? So that's the reason this factor ends up being different. It turns out this is a very nice way to write the solution because this number doesn't depend very much on lambda. And so this fitting formula is good for that. Okay? Then the final thing we can look at is we can play the game you were playing, right? You were saying, what's the nonlinear density in numbers, right? And we can play games with, oh, well, you know, if the thing shrank by a factor of 2, then the volume changed by a factor of 8. But in the time that the volume changed by a factor of 8, the universe was still expanding. So if I want to know how dense I am compared to the background universe, I should account for the fact that it took some time. So the background universe got less dense while it was getting denser. So it got 8 times denser. The background universe, from here to here, took as much time as from here to here. It was a factor of 2 in time. Factor of 2 in time means, well, it's matter dominated, so A is T to the 2/3. And so 2 to the 2/3 cubed, because it should be A cubed. And so 2 to the 2/3 cubed is 4. And so we get a factor of 4 and a factor of 8 from the 2 cubed. Okay? So we know for sure the density is going to be 32 times the background, if not more, because this is 32 times the background, which is the number that it had when it was turning around. And that was already denser than the background. Okay? So to get that number, that's the only number that we need from the exact solution. Okay? And so in the exact solution, the maximum size, this one is telling us the size, right? So the size, we have this parameter theta. And so when it's pi, then that's the maximum that this thing will be. Okay? Because sine is going between 0 and 1, and when we get to pi, this is going back to 0. Okay? So if I just insert here pi, then I will get 9 over 2 times pi squared, and then this guy will be 1 minus minus 1. So it will be 2 cubed. Okay? And so that's the only number that I plugged in. That's the 2 cubed, that was the pi squared, and there was the overall 9 over 2. And so if you plug all that in, right, you plug in this number, and then multiply by 8, and then multiply by 4, then you will get 18 pi squared, which is about 170. Pi squared is 10, so 180. Okay? And so the objects are all 200 times the background density. The nonlinear objects, whatever their mass.
So these are the initial conditions for nonlinear collapse in some sense.
Yeah, so the number that I haven't put here is what did the initial density have to be so that the object would collapse today? Okay? And so when it collapses today, it will be 200 times the background density today. But the initial density that it had to be there was some critical number. The convention is to take that critical number and say, if I used linear theory, so if that number, if the object grew by linear theory, what would it be today? And that number is 1.686. So linear theory says it's 1.686, when actually it's 200. Okay? And so let me just do one more thing, because we were talking about this. That's this one. Okay? So remember, it's very well approximated by this. Okay? And so let's look at what this means. Okay? When the density is small, then I can expand this in a Taylor series. And so I will get 1 plus nonlinear density is 1 plus linear density, because this will cancel this. So it reduces to linear theory at early times, small densities. In the limit in which this one is becoming this number, then this is becoming 1 minus 1, and it's in the denominator. So the density is becoming infinite. So the fitting formula is saying it's becoming infinitely dense. It's becoming 200 times the background density. And when this one becomes negative, which will be like an underdense region, then the linear density, suppose it was, because it can be from a Gaussian field, it can be arbitrarily negative. I'm multiplying by a growth factor, so it can be less than -1. So this can be 1 minus a big number. And so if it's 1 minus a big number, then this thing is becoming 0. And so what this actually looks like the mapping between 1 plus delta and delta, or I should do delta nonlinear and delta linear. Around 0, they are linearly proportional to each other. When this guy is 1.686, this guy is becoming infinite. So linear theory was predicting this, right? That it should always be like this. And this is asymptoting to -1, because it's delta, as this becomes arbitrarily negative. Yeah? So the spherical collapse is giving you a mapping like this. So this is a very handy thing because in the notes or in textbooks of spherical collapse, underdense evolution is treated very differently from overdense evolution. It's the same differential equation, but the sine and cosine become hyperbolic sine and hyperbolic cosine. And so they look like completely different things, whereas this fitting formula does the full range. And it looks like Zeldovich, so it's easy to get physical insight about what's going on. To show you, we've done this very idealized thing of a very smooth object that expands, pulls itself back against the background. Okay? So now I'll show you a movie in which there was a cosmological simulation. In the simulation, we found an object that had collapsed. And then we're going to watch those particles at different output times in the simulation. Okay? Hopefully it will load. Server execution failed. That's not a good sign. Let me try one more time. So I wanted to make a couple of quick points about this, the calculation we just did. And so we said they should all be about 200 times the background density. And we said that, it's failing again, okay. I'll have to show you the movie after lunch, I guess. Yeah. So all objects will be like 200 times the background density. And we have an exact solution which gives the nonlinear density as a function of theta, the linear density as a function of theta, and so we can plot one against the other, or we can write one as a series of the other. So we'll do that in a second. I made the point here that when you set theta equal pi, that's telling us when it got to its maximum size. Theta equals 2 pi is when it has shrunk completely. Okay? And so if in this formula I put theta equals 2 pi, this guy is 0, then I will get 2 pi, 2/3, and this stuff, and I will get the critical value that linear theory says an object has to have to collapse at the present time. And that's where the 1.686 is coming from. Okay, it's this combination of things with 2 pi here. Okay? And then we said, no, formally, if you put 2 pi here, and if you also put the 2 pi here, then this guy is becoming 1 minus 1, which is 0. So that's the density diverging. And that's the one we then say by hand. It doesn't diverge. It virializes at half the turnaround radius. And so that's why the density is 200.
More relevant to say, which is it which virializes today rather than collapses today? I mean, when it reaches the half the radius, when
yeah, so the cartoon is like this, but the more accurate cartoon is steeper. Okay? And if it's steeper, then the difference in time between this and this is not very big, and so we don't pay attention to it. But these are all things that at 1% precision, it might matter, right? So I'm describing the way things are done now, but these are all ways in which things can be improved. Right? And so also this hard chop that the thing virializes and it's 200 times the background density. In principle, you can say there's actually some profile, and that profile means it's one value here, but it goes inside. The whole thing is not 200. So there are technical things that can be done that are interesting to explore. Okay. Okay. And so this is then this expansion, okay? The expansion of the nonlinear density in terms of the linear density. And the only reason I'm putting it up here is to make connection to what we did yesterday when we did perturbation theory. And when we did perturbation theory, then I made the point that perturbation theory you could write as, so the first corrections to linear theory could be written as what is the value of a monopole, a dipole, and a quadrupole. Okay? And so in this one, spherical collapse has no quadrupole because it's a sphere. But the coefficient of the second order term is 17 over 21. That came from doing those things with thetas and doing the expansions, right? And that 17 over 21 is the thing that I said in monopole, dipole, and quadrupole. The monopole is 17 over 21. Okay? And this correspondence holds for second, third, fourth, fifth order. Okay? And so the monopole of perturbation theory is given by that spherical collapse calculation. So one thing that has never been done, remember we talked about how to do, how to organize the terms when we're trying to calculate the power spectrum, the perturbation theory terms, right? And we said instead of organizing them this way, you take out this one exponential piece and then you get a nice ordered thing. No one has done this thing that says, we know how to sum spherical collapse, so we know how to do the monopole completely. We should just do that and then do corrections to that, right? And that's not been done. And that seems like a fairly nice thing to try to push forward. Okay. Especially because we know that the monopole in perturbation theory at any order is exactly the delta to the n term of spherical collapse. Okay, so that's an exact statement. It's not a coincidence.
So you also said that the dipole is missing.
So the dipole is missing. That's right.
I mean, has
Both.
it to do with
So,
the fact that there are no tidal interactions?
Okay, there are no tidal interactions. That's why the quadrupole is missing. The dipole is missing because this is spherical collapse, so we're always doing with respect to the center of the object. If the whole object was moving, we would still be saying everything is collapsing around that center. And so you're in the rest frame of the center, so that's why you don't see the dipole, right? And so one question, which is not answered at the present time, is how important is it to sacrifice the quadrupole and dipole for getting the monopole exactly right? Yeah, so this game has not been played yet. Okay. The other point to make is delta squared in real space means convolution in K space. So this is the coupling of the K modes. because there's the convolution, right? So spherical collapse shows you that pretty cleanly. So this kind of expansion is sometimes called a local expansion, because you could express the nonlinear guy in powers of the linear guy, and no other terms mattered. The shear term did not matter. Okay. This will matter when we want to do bias tracers tomorrow. Right? Then people will use the same language for bias. So it's a little bit ahead, but I just want to use the terminology now. Okay. So there's coupling of K-modes. And in this case, because it's monotonic, that's the shape that I drew over there. So you can ask, if you invert it, then what is the linear density if you have measured the nonlinear density? And so you can, so that means you can play the following game, right? You could take a simulation. In the simulation, you make a grid. You make the histogram. You find out what the values are in each cell. And now you can ask, if I take the deltas, the nonlinear delta, and I map it back to get me my linear delta, do I reconstruct a Gaussian PDF from the non-Gaussian one? No? And if I have done that, suppose I took each value of the nonlinear density and I mapped it back to a linear value, I could measure the power spectrum of that thing. Have I undone nonlinear evolution? Have I undone the coupling of the K-modes? Yeah? And and that's a desirable thing, right? Because it means that when you're testing the theory, you're really always testing whether the linear theory power spectrum is in agreement with theory. The linear theory power spectrum is consistent with the data. And so if you can bring the data back to be more linear, you've gained. And it turns out you do gain. Yeah? Again, people have done the mapping backwards by doing only the first two terms. But it's not very hard to do it with this, because it's the full nonlinear thing. Right? And to just play the game of mapping the histogram back. Now you have a Gaussian-ish histogram, and make measurements of that field. And so there are many places many observables that you can play this game with. More generically, you could ask the question, in data, I have a map of, I don't know, weak lensing signal on the sky, or the thermal SZ effect on the sky, right? And I could just ask, or just number of galaxies in the sky. I want to just map it back to be a Gaussian PDF, meaning I take the densest cell, and so to map back, you will match the cumulative distributions, right? To be the observed cumulative should map to an error function. And you just map this back, and that will Gaussianize the nonlinear field, and you measure statistics of the Gaussianized field. And you ask how well this worked. Yeah?
I have a naive question.
Yeah.
Suppose I consider observed patches, which are large enough so that Zeldovich approximation will be valid.
Yeah.
Okay. And I do this mapping back. Can I map it onto the CMB features?
Not really, because the CMB features are, so it's a good question, and people do this, so we'll come back to that. But the immediate answer is you will map it back to what an observer over there, we are their CMB sky, and you will have mapped it back to what they will see.
CMB.
Yeah, because they're so far, not our CMB. Yeah? But we can play the opposite game. We observe the CMB, and we can say, oh, how should it evolve if we use Zeldovich? We can play that game. Yeah? So some people actually play this game of reconstructing the last scattering surface. What was the structure on there? And people also play this game of, we see where the galaxies are today. We can move them by Zeldovich. So to move them by Zeldovich means we have to know what the density is, because the density is telling us the divergence of the velocities. So then we can switch the sign to move them back. And so you can move them back, and you can see if you can, you remember the BAO bump was smeared out. You can see if you can reconstruct the BAO bump, and you do. And so people play this game. Yeah. There's always a question of taste here. Should you bring the theory into the observed space? So should you be building a model that can correctly model the BAO bump? Or should you massage the data to bring the bump back to theory? Okay? The field currently does both, but the thing that's done more is to massage the data. I don't say because they do it anyway. Okay, so we have the various properties of this mapping. Let's not worry about this. Okay, this was just going through virial, the high density and the overdensity limit. We've done spherical cow approximation, right? And so they're not all spherical. So then we can replay this whole game using Bond and Myers have set this up, and you've worked with this kind of model for the ellipsoidal collapse. Yeah. Okay, then it's a little more complicated because you have 3 axes collapsing. They will collapse at different times, but that's the kind of structure. Okay, and we won't talk about this now. Okay, if you're interested, then we can talk afterwards. And people have explored this kind of model, and always starting from a spherical thing, but because now we have shear, so the 3 axes are collapsing with different speeds. Each of them turns around at a different time, and then you get a final object. Okay. Now you have the same things to ask, right? When this guy turns around, it doesn't really go to 0 size. And so the crude thing that is done is to say this does the same thing, and it freezes out at half the turnaround radius. And then this one does. What's that?
So here you can't look at the energies for the individual axis, right?
Not for the, yeah, because it's a couple thing.
To the entire object.
Exactly, yeah.
So you take a shortcut and you say that at half the turnaround radius.
That's right. Yeah, so it's a very crude thing. Right? So, but that's what's done. Okay? And you do this one, and then you do this one, and then you do this one. And so, okay. Okay, so I wanted to do redshift space distortions, and I got here, so that's good. So here is a thing of the sky. Can I just turn off the lights, because it's a little bit hard to see. Oh, it's here, huh? So this is a map of the Sloan Sky Survey, and we are in the center. And so there are galaxies, the survey looked at some galaxies there and some galaxies there. And can you see that they are like stripes? Okay, so these stripes are there because, you can see an obvious thing like this. This is called the Sloan Great Wall. But even this Great Wall is stripy. Okay, and so the idea is that what's happening is we observe position on a sky, the 2 angular positions, 2 angular coordinates correctly, but the distance from us, we measure a redshift from the spectrum. And the measured redshift has 2 components. It has the Hubble expansion, and then it has the fact that the galaxy can be moving with respect to the Hubble flow because of gravity. And so that the CZ is equal to HD plus a peculiar velocity.
The component of the velocity along.
And it will be the component of the velocity along the line of sight that is distorting the correct position, right? So the correct position should be D. HD should be D. And you're not getting it because you can only use CZ, okay? And so people were aware of that, but they were not sure what effect this has. So now we're in a position to address what effect this has. Okay. So these are generically called redshift space distortions, and I showed this picture on the first day. And so this one is showing the number up here is not redshift. Think of this as a number that you're multiplying all the speeds by. And so if you multiply all the speeds by 0, that's like saying CZ is HD. And if you multiply them by 1, then it's CZ is HD plus the full peculiar velocity. So when you multiply the speeds by 1, then you get nice stripes. And when you multiply them by 0, the stripes have gone away. That's the thing you want, is the one that's gone away. And you don't have it, because you always observe with the full CZ. Okay? And so it's these stripes that we're interested in. Okay. And these stripes are pointing towards the observer in the middle. The Sloan Sky Survey before was a wedge like this and a wedge like that, right? The observer is in the middle, and these are called fingers of God because the stripes all point radially towards the center, towards the observer. Okay?
See, the finger of God should be there if suppose the peculiar velocity, prevails over the HD, right? Others will be flattened transversely.
Okay, so we're going to calculate these two effects. Okay. All right. So the first effect, we will think of, okay, so the two effects, there's going to be a linear effect and a nonlinear effect. Okay, and both have to be added. For the linear effect, let's do Zeldovich. Why do we do Zeldovich? And this is the real beauty of doing Zeldovich. So this is why, even though Zeldovich was wrong, even though Zeldovich is wrong, it's a very useful thing, because if I want to know the redshift space position of something, so that means the position along the line of sight, that position along the line of sight is going to be the real position, distorted by the peculiar velocity. So this is the dot product of the velocity along the line of sight. Okay? And then we divide by h to make a distance. Okay? And so the redshift space position is the real space distorted by a velocity, one component of velocity. But in Zeldovich, this position was itself the initial position plus a velocity, and it's the same velocity in Zeldovich. Okay? The only difference is that in Zeldovich, this velocity comes with factors of f and a, not just h, whereas this one is coming just with an h. Because this one was the full growth, the integral over time, and this one is the speed now. Yeah? And the other thing that is happening, and the other thing that is happening is this one is the full v, and this is the component of v along the line of sight. But it's the same v, okay? And so that means that the trick that we did this morning, that is still on the board there, that we said, if you start from some expression like this, which is a q plus a correction that depends on q, however complicated it is, you can write dx by dq is this delta, plus now this guy will be the derivative of this. And before, and so this has that same structure, right? We have this plus now a complicated function of the q. And before, we didn't have this contribution, we only had this, and now we have to just add this guy. And so we have to take when we take the derivative with respect to q, we'll get a contribution from this guy, and we'll get a contribution from this guy. But the contribution from this guy is going to be very similar to the contribution from this guy, because the only difference is that there's some angle, which is the difference between the velocity it was going and your line of sight. Okay? But otherwise, all the connection between this q and this q is the same. And so the only difference then between these two terms is the factor of f. Okay, so you're going to get the same kind of mapping between the thing that we did to define the nonlinear delta in real space. Now the one in redshift space is going to be the one in real space plus the contribution from this guy. But the contribution from this guy is going to be just like the delta, but now there will be the f, which was missing, and an angle. And the f, because I could put f here, then I have to put f here. And this guy is the angle between v and line of sight, which we're calling mu, is the cos of the angle. Okay? And so the net result is this. That means that the redshift space density fluctuation is the real space density fluctuation enhanced by some amount that depends on the speeds. Okay? So Zeldovich was very nice for this, because it shows clearly that it's going to happen. But you also see why it's not going to be quite right, because we know that the Zeldovich displacement is not quite the right displacement. So if we were now doing effective field theory, then we would be adding the correction term here, and we would have to add a correction term here, because in Zeldovich, the speed today and the integral of the speed over time, that's just some factor of t. Whereas if the speed is changing all the time, is being updated all the time, this redshift space distortion is the current speed, and this one is the result of doing the integral of v dt. So there will be some correction from that. Okay? But other than that, you could just do the same with adding the EFT term, the correction term, and keep track of it that way. Okay? This also means that if I want to do the power spectrum in redshift space, or the correlation function in redshift space, it will be the same as the one in real space, because this number is a number. It's not a function of k. And because it's not a function of k, when I do delta S, Fourier transform of Fourier transform, this is just sitting in front. And so the power spectrum in redshift space is the power spectrum in real space with a different amplitude. Okay? Now, we usually measure, we like to say the power spectrum is spherically symmetric. And this is explicitly no longer spherically symmetric, because the line, the signal along your line of sight is different from the signal across. Okay? But we nevertheless usually measure some spherically averaged thing. And that just means you have to integrate this over the distribution of sine theta d theta, which is d cos theta. So it's uniform in mu. And so we have to do the integral from plus and minus d cos theta. So plus and minus mu of 1, which will give the 1. Then we will get a 2f mu squared, but the average of this will be a 3. And the average of mu squared squared, the 4, will be a 1/5. Okay? And so that's where this is coming from. So this is saying the power spectrum in redshift space, the monopole will be this number times the power spectrum in real space. Then you could measure the quadrupole, which means you come to this expression, and now you multiply by 3 mu squared minus 1 over 2, and integrate over d mu, the Legendre P2. Okay? And you will get different functions of f here. Okay? Why would we do this? Well, we do this because it's going to be, it's different along the line of sight than across, so it will not be a sphere, it will be an ellipse, right, with a long and a short axis. But both of those, the monopole and the quadrupole, will be a coefficient times the power spectrum. So if I divide the two, the power spectrum goes away, and I get something which depends on this quantity f. And Anjan had made the point that this quantity f is like omega to the 0.6. And that is true for all FRW models. And so if you want to check if FRW is right, then that's your check. You didn't have to know what this was to do the check. You take the ratio, it's gone, and you have just some function of this thing. Okay? In practice, yeah. Go ahead.
So when you actually observe, you observe the redshift space
distorted thing, yes.
And to correct that, you have to apply this.
Right, so to correct that, you have to get rid of this factor to get here. But you don't know what this factor is if you don't know the cosmology. If you can take it from Planck, and then you can do it. But we like to check, no? And so, but there's no reason to work with this, if you have lots of objects, then you don't have to do the average over all the angles. You can actually consider separately the pairs along the line of sight compared to the pairs across the line of sight. And the dependence on angle should be given by this function of mu. And so you can check. So that means by checking the dependence on mu, you can try to calibrate what, or try to estimate what this value of omega to the 0.6 is. Yeah? Until now, we haven't had good enough data to play that game. But in the next few years, that's a game that will really be played. Yeah? Is from the angular dependence, do this, rather than simply from the monopole and the quadrupole. Okay. So this was one of the two effects in redshift space. And this, one of the two effects is, was first realized by Kaiser in 1987. Everything that I'll be describing from now on, Kaiser basically worked out. Okay, so the field owes a big debt to him, because he figured out redshift space distortion and he figured out how to do bias. Okay. Okay. It would be nice, it would be beautiful if life were so simple. If you could just divide the monopole and the quadrupole and get F. It turns out it's not, and so let's figure out why. So we know that objects, we expect that they're going to virialize. When they virialize, then what's going to happen? So we said, you know, they're all going to have the same density. The massive objects and the low mass objects. They all have the same density, and so we said, you know, that m over r virial cubed, that's the final density. That thing is 200 times the background density. Okay, so it's just some number. Okay, and that means that if I want to calculate what is the typical speed of a galaxy, then remember, virial theorem means minus w is 2k. And so the typical speed, v squared, is a gm over r virial. Kinetic is potential, factor of 2. Okay? But this will be true for all m, except because they're all the same density, they all have different sizes. So the size depends on the mass to keep the density the same. And so
this is the galaxy on the edge of the halo.
So this is a halo.
This is the halo itself.
This is a halo itself. Okay. So the halo itself is made up of dark matter particles, and we want.
Velocity of the halo.
No. So we're estimating the typical speed of the galaxies in a halo, or the typical speed of a dark matter particle in a halo, because the halo expanded, shrank, and did this. The formula looks just the same as for circular speed, but it's actually just the virial motion. So it doesn't have to be circular speed. Yeah?
Is it dispersion?
It's a dispersion. It's a velocity dispersion. Yeah? But it looks the same because it's the same dimensional argument, right? And so that's what's happening here. It's the kinetic is the potential. Okay, and so this gm over r virial. So I can write the m is 4 pi over 3, 200 times the background density times a radius r virial cubed. R virial cubed over r virial will give me an r virial squared. And the 4 pi g over 3, that stuff will give me h squared over 2, something like that. And so here's the h squared. And then there was the 200 times the background density, that number 200. Okay? So this says the typical speeds will be proportional to the size. Okay, v squared is r squared. Okay, so that's one way to think of this. The other way to think of this is, as a function of mass, are the speeds higher in the more massive objects or lower in the more massive objects? And so in this one, instead of, I tried to write, the crude way to say it is, if m over r cubed is constant, then r is m to the 1/3, which means v squared is m to the 2/3. And so here's the m to the 2/3. So the more massive halos, the more massive objects have higher speeds. They're hotter. That's why massive objects, the clusters, they make hot X-ray gas that we can measure, whereas the small mass halos, if they have gas, it's not really hot to make good X-rays. Yeah? And this all came from the fact that they're all the same density, which came from the fact that we did energy conservation. So energy conservation is really, really powerful, okay? Because there's lots of these scalings now that are coming out as a consequence of energy conservation. Okay, so we have a few things. This is talking about the time, the cosmological dependence, but what does it mean for the virial motions? So we've calculated the typical speeds. And so now if I have a halo, if I have an object like this that is a sphere in real space, and you are looking at it, you don't see a sphere because you see Cz plus Cz, which is Hd. If that was all you saw, it would look like a sphere. But you're seeing an additional component along the line of sight because of the virial speeds. And the virial speeds, they are, let's come back here. My object would be distance Hd plus HR virial. So this is the HR virial, the extra V that you would see if it had no velocity, but it was thick, right? Because it was a sphere, HD plus and minus R virial. But it's 200 times the background density, and so it is elongated along the line of sight by a factor which is the square root of 200, so a factor of 10. Okay? And so these objects, they are typically going to look long along the line of sight compared to across, and this ratio is going to be of order 10. That's the fingers of God.
So basically, so in some sense, the point which is there farther away will switch its side, right?
Okay, so now it could be anything, right? Because now I could have a ball. Virial means that just because a particle is, there's no correlation between the position in the halo and the speed, let's say, right? So I could have a particle here that is moving towards you, or it could be moving away from you. It could be, particles are doing anything, so there could be a particle going this way with one speed, there could be one going this way. It's a full dispersion, right? And so you're going to get a whole dispersion of things, and so it's not just that there's a deterministic mapping. I mean, for each object there's a deterministic mapping, but because it's a beehive of speeds inside the cluster, they're all getting slightly different extensions along the line of, some are going this way along the line of sight, some that way along the line of sight.
So there should be both an effect of elongation as well as this one, right?
Good, so now we have to ask, what was the linear theory one? Because this is the non-linear theory guy. This is the virial motions that are doing redshift space distortions. How does it compare to the Zeldovich guy? Yeah? Because this guy is also going to be along the line of sight, so it's also going to be an ellipsoid. And so now we want to know, this number 10 is competing with this number. Yeah? And another way of saying it is, do we have to worry, how badly are the virial motions contaminating this number? Okay? Okay, so here I was just going through the algebra to give you the factor of 10. Okay? Calling them fingers of God. We'll come back to this. But so the schematic is this, that if you had a cluster with the galaxies buzzing around inside the cluster, then it will look, if the observer is here, it will look elongated along the line of sight. Whereas the Zeldovich thing, if it's an overdense object, it was a cluster that was shrinking. This is doing the kind of thing you were describing. Yeah. So this is doing that. If you're observing from here, then this guy, because it's approaching you, seems to be closer to you than it really is. This guy, because it's receding from you, seems to be further away from you than it really is. And so this thing looks squashed. And so it looks squashed. And so you have two competing effects. One, the linear theory speeds are making everything squashed this way, and the virial motions are making everything extended this way.
Sorry, one more thing. See, when it is becoming elongated, I mean, it is being elongated in the sense it's being smudged as elongated, because there will be some particles will be coming towards you also where you're.
That's right, because here there can be, it's equally likely that this one is going this way, and it's equally likely this one is going this way.
Inside there will be another one which will be smudged like this, but the overall thing will be elongated.
The overall will be elongated. Yeah. And so, so this is the net result of everything. If, very roughly speaking, so these things are virialized, that means that the motions inside are Maxwell-Boltzmann kind of distribution, meaning that they are Gaussian in each of the three spatial components. So along one component, line of sight, it will be a Gaussian with variance 1/3 of the thing we just said, right? And so this distribution of speeds should have a Gaussian shape, more or less, no? And so this is sometimes used to help identify the objects on the sky which are members of the cluster, right? Because remember now, in the sky, there are other galaxies sitting here that are not members of the cluster, because really the cluster is like this. The size here hasn't changed, so really the cluster is like this. And so there are some galaxies here that are not cluster members. And then there are, because of the redshift space distortions, an overlap. And so it's not easy to tell which ones are members and which ones are not. Okay? So the virial motions are a real pain. And so now we have the real question. Do they make it impossible to play this game of trying to measure F from the redshift space distortions? Okay? So if this whole thing is moving this way, then you will get Cz over Cz, the thing you observe, will be Hd plus the bulk motion plus the motions with respect to the bulk. You just add them, right? Because the V peculiar is the sum of all, for each particle, it's the sum of all the components of the motion. So, okay. So here's a measurement of that thing. So this is measuring the pairs of galaxies. So the thing that we were looking at, which was the correlation function of galaxies before, the thing that had the BAO bump, right? So they're doing the same, but now they're classifying the pairs by pairs along the line of sight versus pairs across the line of sight. Pairs along the line of sight versus pairs across the line of sight. Okay? And when you do that, then again you can ask, compared to a random distribution, what is the excess with respect to random? And so the color coding is showing you the excess with respect to random. And so let's look a little bit at this plot. The thing you kind of see immediately is that there's like a purple stripe here. And except for that purple stripe, this is squashed like this. So the squashing is the Zeldovich motions. And this stripe here is the virial motions. The typical halos, we haven't done an estimate yet, but it's 10 to the 15 solar masses. If we take 10 to the 15 solar masses and we plug into, to this kind of expression, then we can estimate these speeds and you get 1,000 kilometers per second. So you get 1,000 kilometers per second for the speeds, and you get that the radii are virial is a few megaparsecs. It's not 30 megaparsecs. And because it's a few megaparsecs, this way is, just a few megaparsecs. So that's why the fingers of God, they're not big things out here. The fingers of God are the typical sizes of the halos. They're long, so they're 30 megaparsecs this way, but they're 3 megaparsecs this way. And so that means that if you can just excise this portion and you analyze here and there, then you can...
Just because our aperture is small, line of sight?
No, it's because the halos are small. So because the halos are small, you could see it in the map. So you can see that the stripes are not fat. They are really stripes because they are 10 times longer than they are thick. Yeah? And that's just that effect. Imagine that plot is basically, if you took each of these stripes and you stack one on top of the other, and then you just measure the typical shape, then that's basically what that is. The correlation function is basically that, right? And so you see the virial motions. The virial motions do contaminate the linear theory calculation, but only at short separations across the line of sight. They contaminate a lot along the line of sight, but only in this narrow bin. So if I take only 10 megaparsecs and bigger here, 10 megaparsecs and bigger here, so I use all of this. So I try to measure the squashing of this, and I don't worry about the distortions to this, which are coming from the fingers of God, then I have some hope of estimating the cosmological signal F. Yeah? And so that's the game people play. So it's clearly a dangerous game to measure the quadrupole of this guy, because the quadrupole is an integral over all the angle. Mu is this angle. It's going to measure all of this, and we'll get contamination from here. But if you can just chop this out, make some new statistic, whatever, then you can measure the squashing and try to measure F. And so that's where constraints in the literature on F are coming from, is from playing this game. There's an important point here, right? So I think someone asked earlier today, with respect to the Hubble flow, so these galaxies are, 300 megaparsecs away from us. So HD is, pretend Hubble constant is 100 megaparsecs per second, 100 kilometers per second per megaparsec. So HD should be 100 times 300. So 100 times 300 is 30,000. So 30,000 kilometers per second. But the typical speeds, the virial speeds, they are much smaller, 1,000 kilometers per second. So when you make a Hubble diagram, for these galaxies, they sit exactly on the line because the 1,000 kilometers per second sitting on top of 30,000 is nothing. So when you think of the Hubble diagram, this is a hopeless thing to measure. But the redshift space distortions, they see it quite nicely. Yeah? And so the redshift space distortions are saying that there is a difference because of the peculiar speeds that depends on F, which is the amount by which the speeds have grown, right? So the omega to the 0.6. What's omega to the 0.6? Omega is 0.3. It's omega matter to the 0.6. Omega matter is 0.3. And so 0.3 to the 0.6 is square root of 0.3. It's like 0.5. 0.5, so 1 plus 1/3 plus 0. Okay? So it's a 1 plus 1/3, so it's a 30% enhancement. So it's a 30% enhancement on, if you're going to throw away scales here, so you're looking on scales that are above 10 megaparsecs, let's say, If you're looking on scales that are above 10 megaparsecs, the correlation function has dropped quite a lot because sigma 8 is of order unity. That means at 8 megaparsecs, the correlation function is of order 1. And so it means you're using only objects where the signal is 1 or less than that. So you need a big survey to measure this. That's why we haven't measured it yet. We've known this for some time, but we haven't measured it yet. We needed a big enough survey to do it. And now that's happening. Yeah. So this is a really promising way to go. And it's really promising also because the way one way of testing modified gravity models is to say, well, what has to happen is that f is omega to the 0.6. That 0.6 can be some other number. In FRW, it can't be. But otherwise, it can be. But more importantly, what happened? Oh. More importantly, the modified gravity models, they are basically saying the way you assembled matter was different from standard gravity, which means all the speeds were different. Because at the end of the day, what you're going to do, you're going to say, I have to get something that looks like the data. And so if you arranged for the distribution on the sky, not in the radial direction, but just on the sky, to be the same as in lambda CDM, then your test is to see if the velocities are different. And so the redshift space is letting you do that. It's letting you do that in an even nicer way as follows. We measure the clustering in bins now of both separation perpendicular and parallel to the line of sight. Okay? Now, we know that the separations along the line of sight are contaminated by peculiar velocities. But so I could do, suppose I take an integral at 10 megaparsecs, I take all these values, I just add them up. So maybe I should take one step back. What is the usual correlation function? The usual correlation function says, I take a circular average. I take the monopole of this. No? So I can take the monopole, then I can take the quadrupole. That's the usual thing. But what I could do instead is I could say, I'm not doing monopole, quadrupole. At fixed perpendicular separation, I'm going to sum up how many galaxies are here. And then I'm going to sum up how many galaxies are here. Because I know that the redshift space distortions are just distorting things this way. The redshift space, the peculiar velocities, they have not changed how many have this separation in total. They've just changed whether they're here or they're here. But so I can just do this sum. So if I do the integral of this for bins in across the line of sight, so let me write this. So I have a correlation function which is parallel to the line of sight and perpendicular to the line of sight. Right? Think of little pixels there. Okay? This thing, if I integrate all these along the parallel line of sight, then I will get a statistic, which is the number of pairs which are perpendicular. This thing is not contaminated by peculiar velocities. And so the real way you'll play the game is you will say, I want lambda CDM to reproduce this, and my modified gravity model to reproduce this. So I will change how I put galaxies in halos, stuff like this, so that this works out, so that they both reproduce this statistic. And now you say, now that I've reproduced this statistic, let me measure the full thing in my theory, in my model, and compare with the data of the full thing, because that full thing now has the peculiar motion effects also. And because the peculiar motion should be different in modified gravity than in lambda CDM, you have isolated that effect in this way. And so this is a very promising way to go, and people will be trying to do this. At the moment, people are fixed with trying to do this just for lambda CDM to estimate F. So there's kind of open space at the moment to do this for modified gravity models.